So today we're going to look at the relationship between free energy and equilibrium. You can see this equation here. I don't need you to memorize this equation as it is. We're going to talk about it and then we're going to rearrange it to look a little bit different. But the free energy of a reaction is equal to the free energy of the reaction at standard conditions, that's what that little knot means, plus RT ln of Q. R being our energy R, 8.31 joules per mole Kelvin, and then Q being our non-equilibrium quotient. Remember, we used Q to figure out direction of shift and so on. So if you are not at equilibrium and you want to find delta G and you know your starting conditions, you can utilize this equation. However, let's pretend we are at equilibrium. We learned the other day that at equilibrium, delta G is 0 because neither the forward or reverse is going to be thermodynamically favored. They both are, so we're on that cusp in between positive and negative. So at equilibrium, the delta G is equal to 0. So if you rearrange that equation, and because we're at equilibrium, that Q turns into a K, because now we know we're at equilibrium, so Q is K. And if we rearrange this, we get delta G is negative RT ln of K. This is the one I want you to know. And the way to remember it, delta G is negative rat link. And you can see above on the board, I have two rats with their tails linked to each other, and that is negative rat link. So let's go ahead and pull all of this into play. Number 11 says, for the reaction, blah, it was determined earlier what the delta G naught was. And so we need to calculate K. We actually didn't do this particular problem in class, so I have my delta G values. I looked them up, and this ended up being a 97.89 kilojoules per mole. And this ended up being a 51.31 kilojoules per mole. If we want to calculate K, and they're asking for K, not Q, so we have to use delta G naught is equal to negative RT ln of K. So we know that the temperature here, we're going to be at 298, and the delta G naught, we're going to go ahead and use Big Mama and calculate it. And so Big Mama delta G, using the at 25 degrees Celsius values, we get 2 times 51.31 minus 97.89, and the unit on these guys is kilojoules per mole. And so when you do it, you get 4.73 kilojoules per mole. I just know that I'm going to need to 730. I'm going to need to be in joules because of my, goodness, could I make a mistake any more than I'm making right now? 4,730 joules per mole. So that's what I'm going to plug into my rat link. So I get 4,730 joules per mole is equal to negative 8.31 right there. That is the reason I need joules, not kilojoules. Times the temperature, we're at standard, natural log of K. All right, so now when you do your division, I'm going to go ahead and divide both sides into this 4,730, and I get negative 1.909 is equal to ln of K. When you're solving for this, I 10 to the both sides to get rid of that natural log. When I go 10 to the negative 1.909, I get a K equal to 0.0123. And this is at 25 degrees Celsius. All right, so that's how you use rat link. Now this next problem says, well, calculate delta G. Notice it doesn't say delta G naught. For the reaction if the partial pressure of NO2 is 0.1 and the partial pressure of N2O4 is 1. Because we're calculating delta G and not delta G naught, we have to use the other equation, where delta G naught plus RT ln of Q this time, because we're futzing with these pressures, and so we are making them not equilibrium pressures, so we have to figure out what they are initially in that Q. So delta G is what we're solving for. We have delta G naught from the previous problem, 4,730 joules per mole, plus R is 8.314 joules per mole K times the temperature of 298. Now, what's with this Q? You treat it just like K, but you do products over reactants. So our product pressure is NO2, 0.1 squared over N2O4 to the first. And there is our Q. So let's go ahead and see what our answer is. When you do this math, you end up getting a negative delta G of 6679. Again, it's negative joules per mole K. So if you look, what happened then to this reaction where our number, what happened to our G? It became spontaneous, right? So when we messed with our values, we went from a positive delta G to a negative delta G, right? So if we're at equilibrium and we become spontaneous in the forward direction all of a sudden, we did a hard right shift, right? Hard right shift. And that's what I'm figuring out just based on what happened to G. We were at equilibrium with a K of 0.0213, and then all of a sudden we're at equilibrium and we have a hard right shift. So let's see if the Q forced a right shift. Our Q, I'm just verifying what our numbers are showing us. Our Q in this problem is 0.1 squared, which is 0.01. Our K is 0.0123. So looking at Q, isn't Q less than K? So if Q is less than K, what is going to happen? Q needs to become K, right? So if Q needs to get bigger, what kind of shift is that going to be? A right shift. And that's why our delta G became spontaneous, because for Q at this value, to get back to being K at that value, we have to shift right. And you can see here, because the reaction became more spontaneous or more thermodynamically favorable, it became thermodynamically favorable, the reaction went ahead and shifted right. So did you need to do all this? No, I just wanted to show you, verify that that Q actually did force the shift to the right, and we can see that as well with the delta G. All right, let's go ahead and do our next problem. It says, consider the reaction. The concentration equilibrium constant for the reaction is 1.12 times 10 to the negative 3 at 750 K. Would you expect this value to increase or decrease at 300? Explain your answer using words. No calculations yet. So, no calcs. We have to think back to our relationship between our endo or exothermic versus the K. Here we have a K that is less than 1. Does everyone agree with that? At 750 Kelvin, our equilibrium constant is less than 1. So go back to your Humpy diagrams and think, what Humpy diagram would we have a K less than 1? K less than 1 means the reverse reaction is favored over the forward reaction. So I want it where it's easier to go reverse than it is to go forward if K is less than 1. So this type of diagram is correct. It's a lot easier for me to go over that hump backwards than forwards. So what kind of heat is this? Heat's going in. We're ending up at a higher heat value, so this is endothermic. Okay. Since we know this is endothermic, we know we'd put the heat here. So the question is, would you expect the value of K to increase or decrease at 300? So 300 means we're taking heat away. Take away, take away, take away heat. If we're taking away heat, which way are we shifting? We're shifting to the left. If we shift to the left, what happens to K? That means we make more reactants. Our K should be smaller at 300 Kelvin than at 750. Again, this is an endothermic reaction because at K is less than 1, the hump would look like this. Since we know the hump looks like this, we know then that this has to be endothermic, which means that I put heat on this side. So the question is, if I decrease to 300, I'm taking away heat, that means I'm shifting left. A left shift means more reactants, which means K should get smaller. So now we're going to mathematically prove this whole thing. To save some time in the video, if I were in class with you guys, I'd have you guys be calculating all this. You're going to get all your values from the tables, and I'm done teaching Big Mama. This is something you guys need to know how to do. If you're struggling and you're worried about it, I want you to verify the values. Using Big Mama, delta H for this reaction ends up being 114 kilojoules per mole, and delta S for this reaction turns out to be 129 kilojoules per mole. So we answered the question. We found our delta H and delta S, again, just using Big Mama. Now it says, using the values obtained in B, calculate the delta G for the reaction at 300. We don't need it at 750. The reason is we already know the K at 750, and that's the goal. Here we're going to find the K at 300 and compare it to the K at 750. So I only need the delta G at 300. And that's what I want us to calculate. So my question to you is, how do I calculate the delta G at 300? Well, I'm going to use Ghetto Homies. Delta G is equal to 114,000. I got to be in joules. 114,000 joules per mole minus 300. That's the temperature K times 129 joules per mole K. When I do the math, I get a delta G of 75,300 joules per mole. So there we go. Why do I need that? I need it for this next part. Now we're going to find the Kc at this particular temperature. This is negative Ratlink, so we're looking for K. So my delta G is 75300 is equal to negative R. R is 8.314 joules per mole. And then my temperature, 300. And then natural log of K is what I'm solving for. When you solve, you end up getting a K of 7.63 times 10 to the negative 14th. And this is a K at 300. Think back, our K at 750 Kelvin is equal to, what was it? It was 1.12. Did we fit our prediction? We said that the K would get smaller at that lower temperature. Is 7.63 E negative 14 smaller than 1.12 E negative 3? Yep. So we predicted correctly. And that's a pretty sexy problem, if you ask me. I like that we did that. All right, so that's it for today's short lecture. We only have one more lecture left for the unit, which is just a little more practice of putting everything together. But feel free to come and ask me questions if you have any.